then its Fourier transform. So the function here, it is defined on the interval minus infinity to plus infinity. So this is the domain of the function. Then we have a function fx. Now the Fourier transform of this function fx is denoted by something like this: f fx. So that is equal to, we are using f bar omega. In Laplace transform, actually what we are doing, we are having Laplace transform of capital Ft, isn't it? So that one we are denoting by fs. Okay, fs. Fs, and which is defined as, sorry, which is defined as how? Integration 0 to infinity e to the power minus st into capital okay. So here the secondary variable is s. Here our secondary variable is omega. Okay, so just match these things. Okay, match the Fourier transform with Laplace transform. Here the kernel is e to the power minus st. Here is equal to minus infinity to plus infinity. F of u into e to the power I omega u into. Okay, so here this is the kernel. That is the kernel. So just compare this and try to understand this. So in Fourier transform, this is the kernel. In Laplace transform, this is the kernel. Here the secondary variable is s. Therefore, we are getting the Laplace transform in s. Here the secondary variable is omega. Therefore, we are getting the function, the Fourier transform in omega. Okay, so this is a different function. Okay, this is a different function. Here we are using capital F and simple s. Here we are using f and f bar. Here we are using f and f bar. Here we are using capital F and simple f. Please try to understand the notations. Okay, please try to understand the notations. Okay, right. So now from this one, okay, so we can define inverse. So inverse Laplace transform of the function fs. We are finding this is actually equal to ft. Here actually we don't have any formula to find this one. We use some techniques to find the inverse Laplace transform. Actually, we don't have a formula in Laplace transform to find inverse Laplace transform. But in Fourier transform, if you want to find the inverse of the Fourier transform, we can use a formula. So inverse Fourier transform of the function f bar omega, okay, which will be equal to our original function fx, which is defined as 1 over 2 pi 1 over 2 pi integration minus infinity to plus infinity f bar omega into e to the power minus, remember there's a minus here, e to the power minus I omega x into d omega. Okay, so that is the formula to find the inverse Laplace transform. Okay, so that is understood. Wait a minute. I omega x. So here actually in Laplace transform we don't have such formula. We don't have such formula. Actually we are deriving this, we are defining this Laplace transform from the Fourier complex integral. Okay, Fourier complex integral. Okay, so if you are given a function, so here possibly you will get a question like this one. Okay, so for a given function, you should be able to find Fourier transform. Okay, hence you may have to find given integral. So we had an example for this one. Okay, using the Fourier transform of a function, we can evaluate integral of some functions. For an example here, so in this question you can see that first question is find the Fourier transform. Find the Fourier transform this function, and hence, so we are using the Fourier transform to evaluate this integral. Okay, so if you find the Fourier transform, you will get a integration similar to this one. So using some substituting some appropriate values, you will be able to find this one. Okay, so in the last class actually we did this question. Today, now you can remember, okay, you can remember that we studied that Fourier, when we study Fourier integral representation, I'm just recalling this for some purpose. When we study Fourier integral representation, so we said that fx is equal to integration 0 to infinity a omega cos omega x plus b omega sin omega x into d omega, where a omega equal to 1 over 5 minus infinity to plus infinity f of u into cos omega u du, and similarly b omega is equal to 1 over 5 minus infinity to plus infinity f of u into sine omega u into so here the function is defined on the interval minus infinity to plus infinity. So that is called the Fourier integral representation of the function fx. Now when fx is defined on 0 less than x less than infinity, then we can find or we can find Fourier sine integral. Fourier sine integral. Function need not to be this function need not to be sorry. This function need not to be odd or even. So we can find sine integral representation for any function. Okay. We can find sine integral representation for any function. How it is defined? Fx is defined as 0 to infinity d omega sine omega x into d omega, where d omega equal to 2 over 5 integration 0 to infinity f of u into sine omega u d. Similarly, we can find the Fourier cosine integral. Fourier cosine integral is defined as fx is equal to integration 0 to infinity a omega cos omega x into e omega, where a omega is equal to 2 over 5 0 to infinity f of u into cos omega u d. Okay, so this is the Fourier integral representation when the function is defined from minus infinity to plus infinity. When the function is defined from 0 to infinity, then you can define something called Fourier sine integral and something called Fourier cosine integral. Okay, Fourier cosine integral. So in addition to this one, we have Fourier complex integral. We have in addition to this one, we have something called the Fourier complex integral. Okay, so here also the range is minus infinity to plus infinity. Actually, we are writing this one, the first one. We are writing the first one, 0 to infinity a omega cos omega x d omega sine omega x in complex form. So that is why we are saying that this is complex integral, Fourier complex integral. How it is defined? Fx is defined as 1 over 2 pi integration minus infinity to plus infinity, minus infinity to plus infinity, f of u into e to the power I u minus x omega e minus x omega du d omega du d omega. Okay, du d omega. So here this is called the Fourier complex integral. Actually this is equivalent to this one. Okay, if you say this is your first one, say this, sorry, say this one is the first one. Actually this one is, and this is second one. Actually first one is equivalent to the second one. Okay, here the second one is in complex form, the first one is in ordinary form. Okay, so actually from the Fourier complex integral we are defining Fourier transform. Okay, from this onwards we are defining Fourier transform. How we are defining? From this onwards we define Fourier transform. How we are defining Fourier transform? We have fx is equal to, from the Fourier complex integral, 1 over 2 pi integration minus infinity to plus infinity, integration minus infinity to plus infinity. Here we are splitting this power I u omega 1 minus I x omega. So we can write it as f of u e to the power I omega u into du. Okay, then we are writing e to the power minus I omega x. So be careful with the variables. Okay, I omega x into d omega. Okay, so this one we call it as the Fourier transform of this function, and we are denoted by f bar omega. Okay, and then from this one so if this is f bar omega, actually this is the inverse of that one, isn't it? So this is the inverse. So finding inverse is very simple. How to find the inverse? And we are denoting this by f, capital F, fx. Okay, so inverse, this is the inverse. We are denoting the inverse by f inverse f bar omega equal to, so we are taking this one, 1 over 2 pi integration minus infinity to plus infinity f bar, because this orange color one is actually f bar, isn't it? This one is equal to f bar, this part. So I'm putting that one because I want fx. Actually I want fx. Okay, I want fx. So here fx is equal to, okay, Fourier inverse Fourier transform of f bar omega, which is equal to minus infinity to plus infinity f bar omega into e to the power minus I omega x into u. So this is called the inverse Fourier transform, right? So this is inverse Fourier transform. So here, look at here, the variable, the range of variable is minus infinity to plus infinity. Now look at carefully, when the range is 0 to infinity, we can define Fourier sine integral. I'm going to talk new thing. Please carefully listen. When the variable is minus infinity to plus infinity, you can define Fourier integral. This one is the complex form of the Fourier integral. When the variable is 0 to infinity, when the function is defined on 0 to infinity, we can define something called, or we can define something called Fourier sine integral as well as Fourier cosine integral. Therefore, what we can do is we can define, or we define Fourier sine transform and Fourier cosine transform. When x is defined on this, okay, similar to earlier. So when the x is defined on 0 to infinity, we can find Fourier sine integral as well as Fourier cosine integral. So similarly, when the function is defined on 0 to infinity, we can define Fourier sine transform as well as Fourier cosine transform. This is called Fourier transform, or we call these as Fourier complex transform. This is called the Fourier complex transform because we are having a now when the function is defined on 0 to infinity, we can define something called Fourier sine transform as well as Fourier cosine transform. Particularly, when the function is defined on 0 to infinity. So how it is defined? We are defining this way. Fourier transform of the function fx, since it's a sine transform, we are putting a small s here. So indicating that Fourier sine transform, and it is defined as okay, 0 to infinity f of u into sine omega u, okay, and this is let me write it, so you can write this as, sorry, it's correct. I just want to add one more thing. So this is defined as Fourier, and we write this as f bar omega. Since it's a sine transform, we put a small s here, and it is defined as 0 to infinity, okay, f of u sine omega u. This is called Fourier sine transform. When we do this one, when the range of x is 0 to infinity. Okay, so inverse of this one, Fourier inverse transform, Fourier sine inverse is f bar s omega equal to 2/5. Okay, so be careful with these things, huh? Sorry for that. 2/5, 0 to infinity f bar s omega f bar s omega into sine omega f bar sine omega into omega x to d. Okay, so this is inverse. Similarly, so this is called the Fourier sine transform. This is called the Fourier sine transform. So if they ask you to find the Fourier sine transform, actually you have to use this one. This one is Fourier transform or Fourier complex transform. This one is Fourier sine transform. So when we can define Fourier sine transform? When the domain is 0 to infinity. So this is called the Fourier sine transform. Now we are going to define, similarly we are going to look at Fourier complex transform, sorry, Fourier cosine transform. Fourier cosine. How it is defined? Fourier. So here also the range is 0 less than x less than infinity. Okay. So it is defined as Fourier transform. Here we put small c because the complex transform of the function fx, and we write it as f bar c omega equal to integration 0 to infinity f of u into cos omega u into du. The inverse formula, inverse Fourier cosine transform, therefore f bar c omega, which is equal to my function fx, which is equal to my function fx. Okay, it is equal to 2 over 5 0 to infinity f bar c omega cos omega u, sorry, cos omega x So this is called the Fourier cosine transform. Okay, so we can define 4 integral. What are they? Fourier integral, Fourier sine integral, Fourier cosine integral. Also, we can write Fourier complex integral. Here, similarly, we have 3 types of transform. Fourier transform, we have 3 types. One is the Fourier transform. Another name for that one is Fourier complex transform. The other one is Fourier sine transform. And the other one is the Fourier cosine transform. So Fourier sine transform and cosine transform is possible when the domain is 0 to infinity. Okay, if the domain is minus infinity to plus infinity, then we have to find the Fourier complex transform. Okay, so this is the formula, you have to use it. Do you understand this one, students? Up to now, do you understand what I am talking? Tell me whether you understand up to now. See, tell me whether you understand or not. What about others? Only one student responded. Are you all there or only one student is available? Okay. Anyway, it's up to you. If you don't understand, please ask me. Now, so it is here, look at how it is defined. Okay, so these are the definition: Fourier sine and cosine transform. So when the range is 0 to infinity, we can define the Fourier sine transform, and this is the corresponding inverse formula. And this is the Fourier cosine transform, and this is the corresponding inverse formula. Now we are asked to find the Fourier transform of this function, not the Fourier transform. We are asked to find the Fourier sine and cosine transform of this function. Okay, now we will work out this problem. Now we are asked to find the Fourier sine and cosine transform of this function. Let's work out on this one. So example, we are asked to find the function is given as 2 to the power 2 into e to the power minus 5x plus 5 into e to the power minus 2x. Okay, so if you look at the function, know any information about the domain, anyway, since they are asking us to find the sine transform and cosine transform, we don't need to worry about the domain because they are asking us. Actually, it is defined for 0 to infinity domain. Okay, only for the half line. But here they are asking, therefore we'll assume that it satisfies that condition. Okay, we'll assume that one. So we'll use the cosine. First we'll find the sine transform. So first solution. So we'll find first Fourier sine transform. Fourier sine transform. So how it is defined? So Fourier sine transform. Let me write f bar omega s equal to. So here it indicates that sine transform. Okay, in this notation, this s indicates that it's a sine transform. Is equal to 0 to infinity f of u. So f of u means this is my function. So f of u means 2 times. So let me write that one before I substitute the value. This is equal to f of u into sine omega u into. Okay, so here my function is 0 to infinity. My function is 2 times e to the power minus 5u plus 5 times e to the power minus 2u into sine omega u into. Okay, so this one you can write it as 2 times integration 0 to infinity e to the power minus 5u sine omega u du plus 5 times 0 to infinity e to the power minus 2u sine omega u. Now, so this integration remind me something. This integration reminds me something. What is that? Can anybody tell me? 0 to infinity e to the power minus 5u sine lambda u. So variable is, instead of t, we have u. Okay, here u, here u, here u. And what is this actually? Can anybody tell me what is this? Yesterday also I told you. Actually, we can evaluate this integration, of course, but we have this one is well known, form. Can anybody tell me what is this? What is this? So this is nothing but at least one student. What is this? What is this? Look at here. What is this? Recall the definition of Laplace transform. Here the variable is, think that the variable here is u. In the place of s, we have minus phi. In the place of a, we have omega. So this is nothing but the Laplace transform of sine omega u, where s is minus 5. Sorry, s is 5 because we have minus st, no? Therefore, we have 5 with s equal 5. Similarly, this one is also Laplace transform of sine omega u with s equal 2. Okay, so you can use this result actually. So this one is equal to 2 into sine omega u. What is the Laplace transform of sine omega? U is the variable. So Laplace transform of sine at is what? Can you remember what is the Laplace transform of sine at? A over s squared plus a squared, isn't it? So here my a is omega, my s is 5. My s is 5. Therefore, this is nothing but omega over my s is 5. Therefore, I can put it omega squared plus 25. S squared because s is 5 plus this one is 5 times. Similarly, omega over my s is 2. Therefore, this is equal to omega squared plus 4. I don't need to find this integration again and again. I can use the Laplace transform thing. So this one is equal to that is the answer. Actually, you can, this is omega squared plus 25. This one is this one. So you can simplify this and get the answer. Okay, so this is the answer of that. Do you understand this, students? So if you want, you can take omega out. If you take omega out, then here you will get 2 omega squared. 2 omega squared plus 8. Plus here you will get 5 omega squared plus 125 divided by omega squared plus 25 into omega squared plus 4. So which is equal to omega into 7 omega squared plus 133 divided by omega squared plus 25 into omega squared plus 4. We'll check the answer. Yeah, that is the answer. Okay, that is the answer. Do you understand this, students? Tell me whether you understand this.
Yes, sir.
Right. So this is the Fourier sine transform. Now what we have got is the Fourier sine transform. Again, they are asking us to find the Fourier cosine transform. So Fourier cosine transform. So we'll use the same formula. F c bar omega equal to integration 0 to infinity f of u into cos omega u du. That is the function. So that is equal to 0 to infinity. Our function is our function is 2 times e to the power minus 5u plus 5 times e to the power minus 2u plus omega u. So if you do the similar way, you can write this as 2 times Laplace transform of cos omega u, where s is 5, plus 2 times Laplace transform of cos omega u, where s is 2. So we know that Laplace transform of cos at equal to s over s squared plus a squared, isn't it? So using the fact, we can write it as 2 times, here our a is omega, therefore 2 omega over omega squared plus 25. Not omega, I'm sorry. That is s, no, s means 5, therefore that should be 10. I'm sorry. So let me put 5. So I'll write this way. This is the Laplace transform. 2 is there. Plus, I'm sorry, here it is 5, no? I'm sorry, it's 5. When I make mistake, please tell me. Otherwise, you will just copy it. 5 into, this one is the same, but here s is 2 over omega squared plus. Therefore, this is equal to 10 times 1 over omega squared plus 25 plus 1 over omega squared plus. So that is the answer. Do you understand, students?
Yes, sir.
Right. So we'll check the answer. Yeah, the answer is that. We have one more question here. Find the function fx if it is Fourier sine transform is this one. Hence, find fs inverse sine Fourier sine inverse Fourier sine transform of 1 over omega. Okay. So here we want to find the function fx whose Fourier sine transform is this one. So actually, what we want to find? Tell me. So if you want to find fx and whose Fourier sine transform is this function, actually what you have to find this one? Can anybody tell me? This is actually, this one is actually your f bar s omega. Now we are asked to find fx. So actually what we want to find? Can anybody tell me what we want to find now? What we want to find? Here we are given this one, Fourier sine transform of a function. We are asked to find the function. So actually what we want to find in terms of subject, tell me what we want to find actually. I am asking the word. Okay, you know, we want to find fx. Actually, we want to find fx. So using this one, we want to find fx. So what is that actually? Finding fx from this one is what is that? What we want to find? Can you tell me in words? Yeah, we want to find the inverse Fourier transform. Okay, inverse Fourier transform. I don't know. I don't get what is this notification when you send the chat. So we want to find the inverse Fourier transform. So next example, we want to find the inverse Fourier transform. So fx is equal to, we want to find the inverse Fourier sine transform, which is equal to f inverse s. The function is given as 1 over omega e to the power minus a omega. So 1 over omega e to the power minus a. So we want to find the inverse of this one. Okay, so definition says what? Definition says 2 over 5. Remember, it is 2 over 5. 0 to infinity, this function. 1 over omega e to the power minus a omega. Okay. Sine omega omega x So this is what we want to find. That is the definition. So if you want, I write the definition also before I write this one. Okay. So that is 0 to infinity. Actually, this is f bar s omega into sine omega x into d omega. That is the definition. So using the definition, we can write it as 1 over 2 over 5, 0 to infinity. My fs is 1 over omega e to the power minus a omega sine omega x into d omega. Okay. Now, actually, you can't take omega out because we are integrating with respect to this one. Okay, integrating with respect to this one. Now, this is equal to 2 over 5 integration 0 to infinity. Let me write this way. E to the power minus a omega sine omega x sine omega x into d omega over omega. So can you tell me what is this? Can anybody tell me what is this? Here our variable is, actually our variable is omega. Our a here is x. This is our a. Look at carefully. This is our a. Okay. This is our t. Omega is our t. And this one is our s. So actually, what is this? This is nothing. 2 over 5 Laplace transform of sine omega x over omega, where s is a. Okay, so that means that Laplace transform of sine Laplace transform of sine at over t. Laplace transform of sine at over t. That is dividing by t. Dividing by t. So can you tell me what is this one? What is the integration of, what is the Laplace transform of this one? Sine at over t. Can anybody tell me? Integration. Can you tell me what is the Laplace transform of sine at over t? Integration. S to infinity, no? Integration. Yeah, S to infinity f of u. Good. So S to infinity f of u. F of u mean Laplace transform of sine. So therefore, this is integration. Our S here is a. Therefore, a to infinity. Laplace f of u means Laplace transform of sine at. So Laplace transform of sine at is actually here x over. Okay, here it is x over. Because our a is x, no? So x over omega squared, not the omega squared, our s squared, no? S is our a squared plus x squared into du. So we have to change this into u. So here our our variable is a. So we have to differentiate with respect to dA. Respect to b, because our s is a, no? Our s is a. So actually that is with respect to f of u. So we have to put this. So yeah, that is the variable. That is the s ds now. So what is this actually? Two over 5. Can anybody tell me what is this? So actually the variable is x. So what is this? So you can take out x. This is nothing but tan inverse x over, where we want to substitute a to infinity. Okay, so let me show the answer. Here, look at here. U is the variable, and we are having 2 over 5. Sorry, x is also there, no? So x is not coming out. So I'm sorry, here x cannot come because what is the integration of differentiation of tan inverse x over a? That should be, I think, tan inverse u over a over x. I'm sorry. So this should be tan inverse. Okay, now if you want, actually, you can change a by u. You can change a by u. If you get a confusion, you can change a by u. Okay, so you can say u squared du, because we are getting the answer in s, our a. Okay, so actually here, if you integrate this one, you will get it in a, because our variable s is a. So this is actually equal to u over x, isn't it? U over x. U over x. Here u is equal to that one. So okay, so you can write this as 2 over 5 tan inverse. So if you put if you put x equal a, sorry, u equal a, okay, if you put u equal s, if you put u equal s, then that becomes if you put infinity, that is 5 by 2. Okay, if you put infinity, the upper limit, no, so that is 5 by 2. So this comes as 5 by 2 because tan inverse infinity equal to 5 by 2. Okay, so 5 by 2 minus, you can put you have to substitute for u, you get here tan inverse a over x. So that is the function. This is the function. Okay, so that is our function fx. Our function fx is equal to 2 over 5 into 5 by 2 minus tan inverse. So understand here, when you find fx, your function should be in terms of x. Here our s is x, because normally when you differentiate it, we get the function fs, isn't it? So normally fs. So here our s is a, no? Therefore, I am replacing a by u and I am getting this answer. Do you understand this one? Hello, do you understand this one?
Yes, sir.
Right. Now, remember this is a over x. Now, again, they are asking us to find this one. F inverse S 1 over omega. Okay, 1 over. So actually, we found fx. We found yeah, f inverse S 1 over omega into e to the power minus a omega equal to, we found that fx equal to 5 by 2, sorry, 2 over pi, I'm sorry, that is equal to 2 over 5 into 5 by 2 minus tan inverse a over x. I'm sorry, a over x. Now they are asking 1 over a. So what is the possible corresponding value for a in order to get the 1 over a? So if you put a equals 0, if you put a equals 0, then we can get the answer, isn't it? If you put a equals 0, then this becomes this one. If a equals 0. Therefore, that becomes 2 over 5, 5 by 2 minus tan inverse a over 0 means 0. Tan inverse 0 is 0. Therefore, this becomes 2 over 5. 5. Therefore, answer is 1. Do you understand this one? Tell me whether you understand this. Do you understand this?
Yes, sir.
What about others? Please respond whether you understand or not. I'm getting response from only few people. I don't know what others are doing. Okay. Anyway, so that is the answer. One. Okay, so letting A equals 0. So here you have to be careful. Okay, about the variables. Okay, you have to be careful about the variables. Now we are having some properties of Fourier transform. So you can remember that we had some properties for Laplace transform. We studied linearity property. We studied change of scale property, shifting property, okay, integration, differentiation, convolution property, and so many things we studied. Okay, so similarly in Fourier transform also we have these properties, but here we are not going to prove this one, okay, and we are not going to use this one, but just to know that these exist. Okay, so here I have put a table. So from this table you can understand that Fourier transform actually satisfy the linearity property. Not only Fourier transform, Fourier sine transform, as well as Fourier complex transform. So all three transform, sine transform, cosine transform, and Fourier transform, or in other words, Fourier complex transform, all satisfy linearity property. You know the meaning of linearity property. Similarly, the Fourier transform satisfies the change of scale property. Change of scale property. All three. Fourier complex transform, Fourier sine transform, Fourier cosine transform. Okay, so if you can remember this one, change of scale property means if Laplace transform of ft equal fs, then change of scale property says that Laplace transform of f of at equal to 1 over a into fs over a. Okay, so similarly here also it satisfies the change of scale property. We are not going to prove this one, but just try to understand this. Similarly, first shifting property. First shifting property. Can you remember in Laplace transform what is first shifting property? That says that if Laplace transform of ft equal fs, then Laplace transform of e to the power at into ft. This is equal to f of s minus. So this is called the first shifting property of Laplace transform. Similarly, here we are multiplying by e to the power iax. We are multiplying by e to the power iax. Then it is coming in this form, f bar omega plus a. F bar omega plus a. Another one is the second shifting property. Second shifting property, we studied that. So it comes in this form. Okay, it comes in this form. Okay, but this one is only for complex, not for sine transform and cosine transform. Similarly, multiplication and derivative property. So this derivative property is important because in a few minutes we are going to discuss application of Fourier transform, where we will solve partial differential equation. In that case, this derivative property is important. This derivative property is important. That means that it says that if the Fourier transform of a function fx equal to f bar omega, then nth derivative of Fourier transform of nth derivative of the function. I'm writing the nth derivative in this way. the nth derivative of this function equal to minus I omega to the power n. N is the order of derivative into f bar omega. Okay, so very simple. Minus I omega to the power n into f bar omega. Okay, so this one is useful. Okay, so in a minute we are going to study this one. Then integral property and similarly the convolution property. Okay, so just we are not going to prove this one. We will not use these things in our questions, but just try to understand that these properties exist for Fourier transform analog to Laplace transform. That means that similar to Laplace transform, we have some properties, not all properties, but few properties are there. If you look at the linearity property, change of scale property, okay, so they are applicable for sine transform, cosine transform, and complex transform. But the first shifting property, similarly, some other properties, derivative property, and these are only for complex transforms. Okay, just understand this one, and you don't need to memorize these things, but just try to understand this one. Okay, because we are not going to use these properties in our exercises, but you must know this derivative property well, because we will use them. Okay, right. Now that's all about the first handout on integral transform, not the last chapter. Yeah, on integral Fourier transform. Now we'll move to the next handout. So here, that's a chapter 2. You will have one more handout. Okay, we have one more section that is called a finite Fourier transform. Here we are talking about the transform in the interval minus infinity to plus infinity. Now, there may be a situation where this is an infinite interval, isn't it? Infinite interval. Sometimes we may have to integrate between, say, minus L to plus L. This is a finite one. So then we have to talk the same thing for finite interval. If we do that, then we are done. Okay. So hopefully in the next class, I will start this one. Maybe another 3 hours or 4 hours, we need to cover this section. Okay. Right. If we finish this handout today, but hopefully we can finish it today if you cooperate. Right. Now we have some identities that is called the Parseval's identities for Fourier transform. Okay, Parseval's identity for Fourier transform. There are a few identities which says that minus infinity to plus infinity fx gx bar. Actually, gx bar, okay, is the conjugate of the function gx, because here in Fourier transform, actually we can use this for complex functions also. We can use this Fourier transform for complex function as well. Okay, complex functions. Complex functions means, say for an example, your function gz may be z squared plus 1, where z is equal to x plus iy. So in that case, this is a complex function. This is a complex function. So if you substitute it here, x plus iy, then your gz becomes what? Or can say that gx comma y. Gx comma y becomes x plus iy all the squared plus 1. Then if you simplify this one, you will get x squared minus y squared, because I squared is minus 1 plus 1 plus 2xyi. So now our function gx is a complex function. So what is the conjugate of this one? Conjugate of this one is x squared plus y squared, sorry, x squared minus y squared we get x squared minus y squared plus 1 plus 1 minus 2xy. So this is the G bar. Okay, so here bar denotes the complex conjugate. Okay, so anyway, we are not going to have complex functions, but just these are Parseval identities that is true for even complex functions. Okay, so it says that, okay, we are not going to prove this one. Just try to understand what does it, what they are saying. That is 1 over 2 pi minus infinity to plus infinity Fourier transform of fx into Fourier transform conjugate of Fourier transform gx is equal to this one. And minus infinity to plus infinity mod of fx squared is equal to 1 over 2 pi minus infinity to plus infinity mod of Fourier transform fx squared. Okay. Similarly, we have the same thing for sine. Okay, 0 to infinity f of gx is equal to 2 over 5 in terms of Fourier sine transform. This one is in terms of Fourier cosine transform. Okay, this one is for the Fourier cosine transform. This one is for the Fourier cosine sine transform. This one is for the Fourier complex transform. Okay, this second one, this one, and this one, they are similar, but this is for Fourier complex transform, or you can say Fourier transform. This is for Fourier sine transform, and this is for Fourier complex transform. Sorry, cosine transform. Okay, same thing. So 1 over 2 pi minus infinity to plus infinity mod of Fourier transform of fx squared is equal to minus infinity to plus infinity, this one. Okay, and yeah, these are there. So just try to understand, and you have to by heart these things. You have to memorize these things. Okay, we have to memorize these things, because using this one, we may have to evaluate, we will have to evaluate some integration. Okay, so using these Parseval's identities are very useful when you have to use when you have to evaluate integration using Fourier transform. Okay, so nothing to prove, or nothing to understand here. Just look at, you can think like a formula. You can think like a formula. Okay, therefore please try to memorize these things, then we will prove this one. So proof is given. Actually, for the first one, the proof is given. For the A part, the proof is given here. Okay, the proof is very simple. You can just go through this one and try to understand, but I will not put a proof for the examination. If you know the Parseval identities, that is enough. If you know the Parseval identities, that is enough. You have to know for Fourier transform, sine transform, and cosine transform. Okay, if you know these things, they are enough. But I will not ask the proof for the examination. Okay, right. So the proof is there for the first part, and you have to do that one. Let's have an example here, and we'll understand how the Parseval identity can be used when we have to evaluate some integration. Okay, right. Find the Fourier complex transform. Here they are talking complex transform. You have to carefully read the question. Complex transform, Fourier transform, all are similar. Okay, Fourier complex transform means our ordinary transformation. Okay, Fourier complex transform of fx. Here, look at the range is this one. Look at here, x belongs to R. That means that the domain is minus infinity to plus infinity. Okay, therefore we can do this one. Here A is positive. So first thing, they are asking us to find the Fourier transform of this function. Then using that one, we are asked to find the integration of this one, but that is also not directly. They are asking us to use the Parseval identity. Okay, so first of all, we'll see. So once you find the Fourier transform of this function, you will get a similar expression in your Fourier transform of this function. Then you just have some idea from the Parseval identity and try to find the integration of this one. We'll see how. So first of all, as the question asks, we'll find the Fourier complex transform of this function. So let me go to my this one. So our function here, fx is equal to e to the power minus a into mod of x. Here a is positive and x belongs to R. X belongs to R. Now we'll find the Fourier transform of this function. So Fourier transform, since it's a Fourier transform, we'll write the Fourier transform. Bar is equal to. We are going to use the definition. So the definition says that integration minus infinity to plus infinity f of u e to the power I omega u into e. That's all. So that is equal to minus infinity to plus infinity. My function is e to the power minus a x, but here I am changing the variable x as e to the power minus a mod u cos, sorry, not the cos, e to the power I omega u into b. Now, since I have mod function, okay, so I'm going to split this integral like this one. So I'm going to split this as minus infinity to 0. So here minus infinity to 0 means in this range, my u is negative. My mod of u is equal to minus u when u is less than 0. Therefore, I'm going to put that one. So minus u means already there is a minus. Therefore, I will get e to the power au into I have e to the power I omega du plus integration 0 to infinity when the mod u equal to u if u is greater than 0. So in that case, if I put that one, then I will get e to the power minus au e to the power I omega u. Then let me simplify this one. Minus infinity to 0. This one, let me write it as e to the power a plus I omega, because my variable is u, du plus 0 to infinity. Let me take minus out, minus a minus I omega u into b. Now if I integrate this one, I will get 1 over a plus I omega into e to the power a plus I omega. I want to put minus infinity to 0 plus this one is minus 1 over a plus, sorry, a minus I omega e to the power minus a minus I omega u. Here also u is missing, I'm sorry. I want to substitute minus infinity to 0. Here I want to substitute 0 to infinity. So if I substitute this value, here when I substitute 0, I will get 1 over a plus I omega minus, when I substitute minus infinity, this part becomes 0, isn't it? E to the power minus infinity becomes 0, therefore that is 0. Here minus, okay, minus. So this minus I put minus here, minus, and when I put infinity, but here look at there's a minus here, therefore that becomes 0. That becomes 0, and here when I put 0, this becomes plus, sorry, minus minus 1 over a plus a minus I omega. Okay, so then if I simplify this one, I get 1 over a plus I omega plus 1 over a minus I omega. So if I simplify this one, actually look at here, these are conjugates of each other, therefore I will get a squared plus omega squared, and the numerator a minus I omega, a plus I omega, so I will get 2a. So that is the answer. Therefore, the Fourier transform of the function, Fourier transform of the function, the Fourier transform of the function fx given function is equal to 2a over a squared plus omega squared. Do you understand up to now, students? Tell me whether you understand.
Yes, sir.
Huh? Right, fine. Okay. Now look at the question here. Sorry. Now they are asking this one. 1 over a squared plus s squared into ds. Okay. So now we are having something that one, but actually we want to evaluate this integration. Integration 0 to infinity 1 over a squared plus s squared whole in square into ds. So now we want to find the answer of this one. Okay, so for this one, we are going to use the Parseval identity. Look at this Parseval identity, this identity. I'm going to use this one because I have square here, minus infinity to plus infinity. Mod of Fourier transform of fx squared d omega is equal to 1 over 2 pi equal this one. So look at here, I'm writing that Parseval identity. A, the second one, Parseval identity. It says 1 over 2 pi integration minus infinity to plus infinity Fourier transform of fx mod squared here I want to tell you one thing. Yeah, that's correct. D omega is equal to integration minus infinity to plus infinity mod of fx squared into. Okay, so now look at here, I want this one. So what I can say is, look at here, from this one, using this one, because this is the Fourier transform of fx, no? My fx I know. So what I can write is, from this one, look at carefully, 1 over 2 pi integration minus infinity to plus infinity. My Fourier transform is actually this one, 2a, this one. So that's a square of that one. Square of that one. So that means that 2a over a squared plus omega squared whole in squared d omega is equal to, according to this Parseval identity, I can say minus infinity to plus infinity. My function fx. So my function is actually e to the power minus a mod x. So what is the square of this one? What is the square of this one? Can anybody tell me what is the square of this one? Can anybody tell me what is the square of this one? Is equal to? What is the mod of this one? What is the mod of this one? Okay, what is the mod of square of this one? You can write this as using the, we know this one, using the identity, we know this one. A to the power m to the power n is equal to what? Those of indices, a to the power mn. So using this one, you can write these as e to the power minus 2a mod x. Minus 2a mod x. Is it minus 2a mod x? Therefore, here you can write this as e to the power minus 2a mod x into. Now I'm erasing this one. So actually what we want is 1 over a squared plus s squared d omega. So omega here actually in the question, instead of omega we have s. So here variable is also s. Integration with respect to also s. But look at here, this is 0. But there we are having plus infinity to minus infinity. Okay. Let's see what else we can do with this part. Okay. So this implies now I can take this 4a squared out because that is independent of omega. So if I square this one, then 4a squared over 2 pi, that becomes 2a squared over pi. Okay. Integration minus infinity to plus infinity. 1 over a squared omega squared whole in squared d omega is equal to this integration. So how can I write this integration actually? So I can split this integration minus infinity to 0 1. In that case I will have e to the power 2ax because x is positive, x is minus x, plus I can put here 0 to infinity e to the power minus 2ax. Why I want to put minus 2ax? In the positive range, this is plus. Therefore, here it is when I put 0, that becomes 1, and this is 0. This is when I put minus infinity, that becomes 0. Plus, when I put infinity, that is 0. Here it is yeah. When I put 0, anyway, I'm making mistake. Minus 2. Yeah. That's correct. So where I'm making mistake. So wait a minute. I'll check that one. Where's the mistake? I didn't get it. Yeah, minus 2a mod x. This range minus infinity to 0, that is 2ax. That's correct, no? Because when x is in this range, it is minus x, no? So minus x means plus 2ax. That's correct. And here in this range, it is minus x. There, sorry, plus x. Therefore, 2ax. So minus infinity to plus infinity 2ax. And here 0 to infinity minus 2ax. So when I put 0, I get 1 minus when I put infinity, that is 0. That's correct. Plus here, when I put infinity, that becomes 0. When I put 0 minus 1. So can you check this one, please? Because this is becoming 0. But we want to find the answer is given 4 over 5 over 4 pi cube. So can you check this answer, please? Where's the mistake? I didn't get actually. I'm sorry. Yeah, we have to integrate it. Yeah. So we are integrating it now. So I think, yeah. Thank you. So mistake is there. Sorry. We didn't integrate it, no? We haven't integrated it. So we have to integrate it. So if we integrate this, this becomes 1 over 2a e to the power 2ax minus infinity to 0 plus minus 1 over 2a e to the power minus 2ax 0 to infinity. Okay, so then if you put 0, then that becomes 1 over 2a. And if you put infinity, that becomes 0. Here minus is there, minus 1 over 2a. And if you put infinity, that becomes 0. Here it is minus 1. So finally we are getting minus minus. So 1 over 2a plus 1 over 2a, which is equal to 1 over a. So we are now having this one. We are having here 2a squared over 5. But look at the integration is not 0 to infinity. Still we have minus infinity to plus infinity. 1 over a squared plus omega squared. It doesn't matter. It's just a matter of variable. Squared d omega is equal to 1 over a. Now, how can I change this to 0 to infinity? Can anybody tell me? But we can't just change this one. But if you have any idea about this function, we can change this one. Actually, if you look at this function, this is what kind of function? Can anybody tell me this is what kind of function? Can anybody tell me this is what kind of function? Yeah, it's an even function. Since it's an even function, so you can split the thing, and but you have to put 2 here. Then that becomes 4a square over 5. Then this integration is from 0 to infinity. 1 over a square plus omega square whole square is equal to 1 over. So that implies integration, because the reason is this function is the even function. We studied the definition of even function. Okay, so then that becomes 0 to infinity, 1 over a squared omega squared whole squared into the omega is equal to 5 over. Actually, in the question we have s, but anyway, you can write that one. So you can say 0 to infinity, 1 over a squared plus a squared into ds 5 over 4. Okay. So you understand this, no? Right. So actually, today it's not possible to start the this one application to boundary value problems. Actually, I thought of completing this also, but time is not enough. So I actually today I had a discussion with Faham sir regarding your academic calendar. Then he said that actually before this ongoing strike starts, we had some holidays, and even before we had some strikes. Therefore, the plan actually the academic they supposed to extend the your academic calendar. Therefore, we have 2 more weeks. We have 2 more weeks something. Okay. Therefore, he said that we can continue the lecture next week and week after next. No problem. Until the faculty reopens, he said that we can continue the lecture. He also didn't finish his syllabus, so he told me that we can continue. Therefore, we don't need to rush. Anyway, tomorrow we have 3 to 5 real analysis. Before that, do we have any time? Because 3 to 5, if it is odd time, then we can have it in the morning if you wish, or we can have it from 1 to 3 or something if you wish. Because tomorrow night is not possible for me. So if it is possible, we can have real analysis little early in the sense that we can have it in the from 1 to 3. Just if you don't have any lectures, please let me know. Then we can schedule real analysis little early and we can finish it. So I think we need another 2 classes for Fourier transform and 2 classes for real analysis. Okay, if everything goes according to the schedule. Or sometime we need one more classes. Okay, so anyway, after the festival, we will have 1 class tomorrow, and if possible, Friday also. If we can have 1 class, then anyway, I will put that request on the WhatsApp group. And if you all are free, please let me know. Then we can have some. We can utilize the free time. I know the festival is coming, and you Muslim students maybe you may be getting ready for festival, celebrating the festival. And I think next Friday, I think Fasan is coming, no? Single students, I think Fasan is coming. So you also may be busy with that thing. So we anyway, if it is next week, if you all are busy with the festivals, then no problem. We can hold on our lectures, and week after next we can discuss. So what I am thinking is tomorrow we will have one class. If possible, Friday also we'll have one class. Then we can somehow balance it, and after festival week, if we can have one or two lecture on real analysis and this one, then we can finish the syllabus, and later we can do some tutorials. Once I set the paper, I can discuss the structure of the paper with you. Okay, so that's all for today. I will send the tutorial for this one. Okay, for the real analysis also I want to send you some tutorial. But we have done enough questions. Okay, therefore you don't need a separate tutorial. But anyway, for the sake of having tutorial, I will send tutorial for integral transform. Real analysis also I will send some questions for that is expecting questions for your final exam. Okay, so that's all. Thank you for giving this time, because more evening I was somewhat tired, so I couldn't have lecture. So